Okay, so if you've ever dipped your toes into statistics, you've definitely heard of the t-test and the z-test. They sound almost the same, right? But here's the thing. Picking the wrong one can completely tank your analysis. So, what's the real difference, and how do you know when to use which? Let's get into it. Imagine this. A new drug is tested on 20 patients, and hey, it looks like their blood pressure went down. The stakes here are massive. Did the scientists discover a breakthrough, or was it just a fluke? This is exactly the kind of high-stakes question that these tests are built to answer.
So here's our game plan. We're going to start by meeting our two tests. Then we'll figure out how to make the right choice between them, and this is the important part, understand why that choice matters. After that, we'll look at some real-world examples and finish up by packing your statistical toolkit.
All right, let's meet our two data detectives. You can think of the t-test as the super cautious investigator, the one you call when you've only got a few clues. The z-test, on the other hand, is like the veteran who's used to working with mountains of evidence. They're both chasing the same truth, just in different ways.
Now, the job they both share is called hypothesis testing. It sounds technical, but it's really not. All it means is testing an idea. For our drug company, the hypothesis is this drug works. These tests help us look at the data from those 20 patients and decide, is this a real meaningful effect, or could this have happened just by random chance?
So, what's their shared mission? Well, at their core, both tests are all about comparing averages, or means. You might be comparing the average of one group to some known number, or you might be comparing the averages of two different groups to each other. Either way, the goal is always the same: to figure out if the difference you're seeing is actually a big deal. Okay, so if they're both comparing averages, how in the world do you know which tool to pick from your toolkit? Well, it turns out it all comes down to asking just two very simple questions. Here it is, the two-question rule. First, you ask yourself, is my sample size big? And in statistics, the magic number is usually considered to be 30. Second question, do you happen to know the standard deviation, which is just a measure of how spread out the data is for the entire population, not just your little sample, but for everybody? And this table really breaks it down perfectly. You reach for a t-test when you've got a small sample, fewer than 30, and when that population standard deviation is a total mystery. You use the z-test when you've got a big sample, or in those really rare situations where you actually do know how spread out the data is for the entire population. But why? Why is 30 the magic number? And why do we even need two different tests to begin with? The answer to this is the key to really getting it, and it all has to do with the shape of uncertainty. Think about it. With a really small sample, like our 20 patients, there's just more uncertainty, right? We can't be totally confident that this small group is a perfect snapshot of everyone. And that's exactly why the t-test was invented, to be a kind of statistical safeguard when we're dealing with that uncertainty. So, how does the safeguard work? Well, the t-test uses a special curve that has what we call heavier tails. All that means is that the test is naturally more skeptical. It assumes that weird, extreme results are more likely to happen just by random chance. So to convince a t-test that what you found is actually significant, your evidence has to be that much stronger. It's a fantastic protection against being fooled by a fluke. Let's actually watch this play out. With a tiny sample, let's say just 5 people, the t-distribution is really flat and wide. See how the ends, the tails, are thick? That shape is literally a picture of high uncertainty. It makes it harder for any single result to seem surprising because so many different outcomes seem possible. Okay, now watch what happens as we collect more data. Let's bump our sample up to 15. See that? Our uncertainty starts to shrink, and the curve gets taller and thinner. The tails get lighter. It's starting to transform. It's looking more and more like that classic bell curve that the z-test uses. And finally, the big moment. Once our sample size hits 30 or more, the transformation is pretty much complete. At this point, the t-distribution and the z-distribution are so similar they're practically identical. Our uncertainty has gotten so small that we just don't need that heavy tails safeguard anymore. And that convergence is exactly why 30 is such a famous rule of thumb.
So now that we've got the theory down, let's put it into practice. Where do our two data detectives actually show up in the real world? Let's compare two totally different scenarios. On the left, we've got a clinical trial with just 20 patients. Samples are small, they're expensive, and the t-test's built-in skepticism is absolutely crucial. You need rock-solid proof. Now, on the right, you have a tech company testing a new button on their website for millions of users. The sample is enormous. Here, the z-test is the perfect, efficient tool for spotting even a tiny but meaningful improvement.
All right, let's wrap this all up. It's time to pack your statistical toolkit with the final key takeaways so you're ready for your next analysis.
Here it is, your quick guide. If you somehow know the standard deviation for the whole population, which almost never happens, go with a z-test. If you don't know it, which is pretty much always, then you look at your sample size. If it's less than 30, the t-test is your champion. If it's 30 or more, the z-test is a totally reliable and often simpler choice.
So let's end on this thought. That rule of 30 isn't some magic spell. It's just a reflection of uncertainty. It's a guide for when we can start to feel more confident in our data. So the real question to ask yourself isn't just which test should I use, it's how much certainty do I actually have in my data? Because choosing the right tool always starts with honestly answering that question first.